Hello everybody, welcome to today's physical sciences lesson. I am Clinton van der Venter and I'll be going through some important grade 10 chemistry yet again this week. The last couple of weeks we started to speak about some specific calculations that you need to do, and we are touched on the mole concept. The mole is the amount of substance. And we're going to be using that idea, and we learned about how to calculate the number of moles of something. So, for example, you could have 2 moles of oxygen or 2.5 moles of carbon dioxide, whatever. And that number of moles is really important for all the calculations we have to do. And now there's quite a few, and they form the basis for all the calculations you're going to be doing in grade 10, well, in grade 11 and 12 physical and chemistry as well. So I hope that you find it helpful and interesting. And these calculations are worth quite a lot of marks. So, and they're not too, they seem complicated, but if you pay attention and make sure that you embed the fundamental concepts, then they're actually not too hard. They're actually quite easy. So we are looking at quantitative aspects of chemical change. So we are now looking at chemical reactions and chemical equations, and we are measuring and we are working out the mass or the volume or the number of moles or the concentration. And I'm going to do a lot of examples today and show you how to perform these calculations. So we refer to the periodic table because in order to work out the number of moles, we need to have mass divided by molar mass. So in order to get the molar mass, we need to look at the periodic table. And we look at the relative atomic mass on the periodic table to work out the molar mass of a element or of a compound. Okay, so I've just put a chat so that we can keep referring to it if we need it. So it'll helpful for you when you're doing these calculations to have access to a periodic table. There's always one in the textbook, and hopefully your teachers have given you one. Otherwise, you won't be expected to do these calculations without a periodic table. So in the test or an exam, you would have to be given a periodic table as well, because you can't learn all those numbers off by heart. So just to quickly summarize, we spoke about the mole concept, and we said 1 mole is 6,02 times 10 to the power of 23 particles of that thing. Okay, and that's called Avogadro's number. And it's like having a dozen. A dozen means 12, but a mole in chemistry means 6,02 times 10 to the power of 23, which is a very, very big number, which makes sense because we're dealing with atoms and molecules. Okay, so we've already learned how to work out the number of moles. Okay, and the number of moles is equal to the mass divided by the molar mass. Okay, so small m divided by capital M. Small m stands for mass in grams, and capital M stands for the molar mass, okay, which is grams per mole. And that's what we get from the periodic table. So now we're going to look at calculating the concentration of something. Okay, so this is a very important formula that we learned how to use over the last 2 weeks. And now we're going to learn how to work out the concentration. And it involves the number of moles. So that was a very important concept to bed down. So this number of moles is really, really important. Okay, so the concentration of something is expressed, C is equal to, so that's a small c, N over V. Okay, concentration is the number of moles divided by the volume of whatever the substance is that we, so this is usually got to do with liquids. We usually calculate the concentration of a liquid. It sometimes can be of like gas mixture, etc., but it's generally of liquids. So like if you think about making yourself a juice or an Oros, if you put a little bit of Oros and a lot of water, it's not very concentrated. But if you put a lot of Oros and only a little bit of water, it's going to be very concentrated and very sweet. So that's the same concept that we learn now in chemistry. So I'm just giving you this triangle over here. So if we want to work out C, then C is N over V. But if we want to work out N, then it's C times V. And if we want to work out V, then it's N divided by C. That's how those little triangles work. It's just a helpful little handy thing, so you don't always have to change the subject of the formula. but we're still going to be using this first equation a lot. Where's my highlighter? Let me get a... so we're first going to be using this equation a lot still, how to calculate the number of moles when we are given the mass. Right, so let's do a little example. The mass of 20 grams of sodium hydroxide, so that's NaOH, is dissolved in water to form 200 centimeters cubed of solution. Okay, calculate the concentration of this solution. Right, so I'm going to show you how to do this now. We're going to get our pen and we're going to say we got to calculate the concentration. So before we calculate the concentration, we see that we need N divided by V, but we don't know what N is. Okay, we don't know what the number of moles is. It only tells us what the mass of sodium hydroxide is. We've got 20 grams, so we've got to use our other formula first. I'm going to just erase this for now. We're going to go and do our other formula. Number of moles is equal to mass divided by molar mass. So the mass, they gave it to us generally in the question, it's 20 grams. Now the molar mass of sodium hydroxide, now we've got to go and double check that on the periodic table. So sodium, we've got to go check on, oh, sorry. Sodium is 23, oxygen is 16, and hydrogen is 1. That's where I'm getting these numbers from. Okay, even I don't know them always off by heart. So the molar mass of sodium hydroxide would be 23, because that's sodium, oxygen is 16, and hydrogen is 1. So we would have to add that all up. Okay, and then we would just work that out on our calculator. We would say 20 is the mass divided by the molar mass. So it's 23 plus 16 plus 1. You can put that in brackets in your calculator and work it out for you. And we get half, okay, or 0.5. That means we have 0.5 moles of sodium hydroxide. That's how many particles of sodium hydroxide there is. Now we can work out the concentration, because concentration is equal to the number of moles divided by the volume. And we've just worked out the number of moles, it's 0.5, okay? And the volume is given to us, the volume is here, it's 200 centimeters cubed. Now, there's a little trick, okay? When we're dealing with volume in these concentration calculations, we need to make sure that it is in decimeters. So, sorry, that centimeters cubed should be written as centimeters cubed with the little 3 on top, okay? Now that should be in decimeters cubed, which is just another way of measuring, just like you can measure something in centimeters or in millimeters or in meters or in decimeters. Okay, so now there's 10 centimeters in a decimeter. So we would have to take that 200 centimeters cubed and divide it by 1,000. That's the rule for converting centimeters cubed into decimeters cubed. You're always going to divide by 1,000. Okay, because when we do these calculations, you must always have your volume in decimeter cubed. Okay, always, always, always. That's the rule. So it's a little trick there that you've got to remember. You can't just use that 200 straight away. So now we're going to say 0.5 divided by that 200 divided by 1,000. Okay, and you can put it in brackets on your calculator. And we get 2.5. Okay, so what is the units for concentration? Well, if you look at how we work out concentration, it's number of moles divided by volume. Number of moles is moles and volume is decimeters cubed. So the unit for concentration is, sorry, let me rub that out. The unit for concentration is moles per decimeter cubed. Moles per decimeter cubed. Sorry, that 3 looks a bit funny there. And that should be a -3 because it's per. So another way to write it is to do this: moles per decimeter cubed. Okay, or you could write it as mole times decimeter to the power of -3, which means divide. Okay, so it means the same thing. Both of those notations there mean the same thing. So that means the same as that. Okay, so whichever one you prefer. I think generally, I know in the IEB syllabus, they prefer the second one, the times decimeter to the power of -3. And I think it's the same in the caps. So maybe get used to that second one rather. So that's how you work out concentration. You need the number of moles and then you need the volume. And you've got to make sure that the volume is in decimeter cubed. So if they give it to you in centimeters cubed, you are going to convert it into decimeters cubed. Okay. And then just some terminology to learn and to study. When I mix something with water, say, or any other liquid, that is, I can make it concentrated. So if you look at this picture down below here, okay, if I use a lot of that and a little bit of water, I will get a high concentration. If I use a little bit of that and a lot of water, I'll get a lower concentration. So whatever you are mixing, whatever you are concentrating, that is your solute, and you mix it in your solvent. And that is when we're talking about a solution. Okay, so that whole mixture is called a solution. So think about your Oros or whatever juice that you mix at home. This is your solute, and the water that you put it in is your solvent. And that mixture together is called a solution. Okay, and what is the volume that we are talking about? We're talking about the volume of that water that is in that solution. Okay, so that volume there, we would have to know how much that is. So that could be in liters, it could be in centimeters cubed, it could be in decimeters cubed. We always need to make sure that it is in decimeters cubed. And remember, decimeters cubed is the same as 1 decimeter cube is the same as 1 liter. But we've got some examples, I think, on that. Okay, let's talk about volume. Okay, we also need to calculate the molar volume. So now we spoke about concentration. It's a number of moles divided by volume. Now we're going to talk about what is volume exactly. Okay, and this is particularly pertaining to gases. So molar volume, and this is a new term that you now have to learn, just like we learned what molar mass is. It's the mass of 1 mole. So molar volume is the volume of 1 mole of something, and this is usually has to be a gas. Okay, so the molar volume is the volume of 1 mole of gas. Okay, and this is quite nice and easy to remember. It doesn't change all the time like mass. 1 mole of any gas is always 22,4 decimeter cubed. Okay, decimeter cubed is just what we measure volume in. It's always 22,4, but it has to be at STP. So I don't know if you know what STP is. STP stands for standard, I've got it over here, standard temperature and pressure. So standard temperature is 1 atom. 1 atom is a unit we use to measure temperature. There's other units as well, millimeters mercury, which is we don't use often, and then 101,3 kilopascals. Pascals is another unit we use for pressure. You'll see that at any of the like petrol stations, and you want to put in air into your tires, say, then that's in pascals or kilopascals. And then temperature, standard temperature, it's not room temperature. Room temperature is 25 degrees. Standard temperature is 0 degrees Celsius. And another way to measure temperature is in Kelvin, 273 Kelvin. It's not degrees Kelvin, it's just Kelvin. And you'll learn more about Kelvin in grade 11. I wouldn't worry about Kelvin now. It's just another way that we measure temperature, especially in chemistry. There is another way we measure temperature, which is Fahrenheit, degrees Fahrenheit. And that's what they use like in the USA. That's just another unit. But Kelvin is something we use in chemistry, but we don't really focus on that in grade 10. We only start looking at that in grade 11. So that's what standard temperature and pressure is. Okay. So at sea level, like I'm here in Durban, that's standard temperature. It's normally 1 atom. And then if you go higher, your pressure can change. So generally, we're going to do always these calculations at STP. The question will say at STP. So what is 22,4 decimeter cubed? Just so that you have an idea of it, it's like a 25-liter bucket, okay? Liters are the same as decimeters cubed. So obviously a 25-liter bucket is just a little bit more than 22,4 liters. But if you can picture what a 25-liter bucket does, or maybe you've got it there, you use it to wash the floors, etc., or in the garden or whatever, that's just an idea of what one mole of something is, the volume of 1 mole of something. So any gas, no matter what gas it is, oxygen or carbon dioxide or neon or argon or any gas, hydrogen or helium, any gas, 1 mole of any gas is always going to be 22,4 decimeters cubed if it's at STP. And we will only work with STP. Right, so let's do this calculation here. We're going to determine the volume of 2 moles of sulfur dioxide. That's the gas, sulfur dioxide, at STP. So you see the question tells us it's at standard temperature and pressure. That's what STP stands for. And this is another little triangle that tells us how to work out the volume. Okay, so number of moles is equal to also the volume divided by the molar mass. So if I wanted to work out the volume, if I wanted to change this triangle, volume is equal to the number of moles times by the molar mass, N times capital M. Okay, so do we have the number of moles in this example? Yes, we do. We don't have to go and work it out. We've got the number of moles. Now all we need to do is work out the volume. So V is equal to number of moles times by, remember there's a dot or no sign, it means multiplication. Number of moles times by capital M, which is molar mass. So the number of moles, they told us in the question, it's 2. Now we've got to work out the molar mass. Now remember, we always get the molar mass from the periodic table. So remember, oxygen was 16. Sulfur, on the other hand, we better go and check what sulfur is. Go back to the periodic table. Sulfur is 32. There it is, 32. That's what the mass of sulfur is. And oxygen is 16. So the molar mass of that is going to be 32 plus 16 plus 16, because there's 2 oxygens in that formula, SO2. That's what O2 means, there's 2 oxygens. So let's maybe just work that out. 32 plus 16 is 64. Okay, so 2 times 64, that's going to be 128. So that's the volume . Oh no, I'm telling us a long way to do this, and we don't even need. There's such a quick way to do this. Let's rather work it out like that. Sorry, it's not moles. It's not. Goodness me. It's number of moles times volume equals number of moles times the molar volume. Okay, so I need that to go away. Molar volume, sorry, we just spoke, I read that wrong. I thought it was molar mass. It's molar volume. Okay, so forget what I said about the molar mass. Molar volume. So molar volume is sometimes with a little m there, Vm. So we've got 2 moles, and what did we talk about? The molar volume, sorry, you don't need the molar mass to work this out, is 22,4 decimeters cubed. So if I've got 2 moles, then it's simply 2 times 22,4 decimeters cubed. It's as simple as that. So we don't need to work out the molar mass. Sorry, I misread that formula. 2 times 22,4 is 44,8. 44,8. And that's going to be decimeter cubed, because volume is measured in meter cubed. That's the standard way to do it. Volume is equal to number of moles times molar volume. 2 times 22, 4. It's 44 decimeters cubed. Okay, so make sure you read that properly, not like me, who read it incorrectly. So that's how you work out concentration now, that's how you work out the volume. Now this volume is normally for gases. Okay, any gas at STP is always 22,4. So you don't really need a formula if you think about it. If I've got 1 mole, it's 22,4. If I've got 2 moles, then it's 2 times 22,4. If I've got 3 moles, then it's 3 times 22,4. Let's try another one. Determine the volume of 12,4 grams of carbon dioxide. Okay, so now they just made it a little bit more harder. Because they didn't give us the number of moles of carbon dioxide, they gave us the mass of carbon dioxide. Okay, so this is when we need to have the molar mass. In order to work out the volume, we need to know the number of moles and we need to times that by molar volume, which is 22,4. But we don't know what N is. So we've got to first work out the number of moles. And we go back to our original formula. Number of moles is equal to the mass given divided by the molar mass, which is from our periodic table. So the mass given is 12,4. That's in the question. And then the molar mass of carbon dioxide. So I know that carbon is 12 and I know that oxygen is 16. So it's going to be 12 plus 16 plus 16, which is 48, I think, 44. Okay, so we first have to work out the number of moles. 12,4 divided by 44. So that's 0,2818. So we can round off to 2 decimals. Okay, now that's not our answer because the question said we must calculate the volume. Okay, so now we've got to go back to our original idea of working out volume. Now that we know what the number of moles is, now we've just worked out N. Now we need to work out the volume. So we're going to say volume, therefore the volume is 0,28 moles here, 0,28 times by the molar volume, which is 22,4. 0,28 times 22,4. And I get 6,3. Let's round off to 1 decimal place. You would follow the instructions of whatever the paper is or the question. So 6,3, and then what is that going to be? It's going to be decimeter cubed because volume is measured in decimeter cubed. Okay, mass is measured in grams, N is measured in moles, C is measured in moles per decimeter cube. Okay, so you do have to learn that so that you don't get confused while you're busy. Okay, so there we go. We've worked out the volume, but we first had to work out the number of moles. So that mole concept is really, really important because everything goes back to number of moles. Now we're going to go on to the stoichiometric calculations. Okay, stoichiometry. It's a fun word to say, and that's how you spell it. Stoichiometry. It's calculating quantities in chemical reactions. Okay, hence the title of this whole section of work, quantitative aspects of chemical change. It means that we are basically calculating quantities. And what are quantities? Well, it's what we've spoken about. It's number of moles, or its mass, or its volume, or its concentration. Those are all the quantities that we are talking about. Okay, so it sounds fancy, and it is actually. Okay, these calculations can be a little bit difficult, but I'm going to walk you through it. And if you understand the fundamentals, then it's not going to be so hard. Okay, so before we begin, it's very important for us to realize that whenever we have to do a stoichiometric calculation, calculate the quantity of anything involved in the chemical reaction, we have to have a balanced chemical equation to work from. It has to be balanced. It has to be correct. Okay. And remember, the balanced chemical equation means that the amount of reactants is equal to the amount of products. Okay, whatever I start with is what I have to end with. And I'm going to talk more about it as we do examples. But your first step is to write a balanced chemical equation. So you need to know how to write formulas. You need to know how to balance chemical equations. And we're going to get some more practice as we're going along. Okay. So stoichiometric calculations work on the principle of the law on conservation of mass. It's that the mass of all the reactants is equal to the mass of all the products. Okay, on the one side is equal to the other side. That must be true of any equation, okay? Even a mathematical equation. If you have an equal sign in between, then it means whatever's on the left has to be equal to whatever is on the right. Okay, so always, always, always work from a balanced chemical equation. Let's get down to some examples. Right. Here's an example where we are going to be calculating the mass, okay, which is measured in grams. So when iron ore, that's when you're mining iron, okay? So what is iron ore? It's containing iron 3 oxide, is reduced by carbon monoxide in a blast furnace. Iron and carbon dioxide are formed, all right? So they're giving us this like maybe seemingly complicated sentence, but all we have to do is write a balanced chemical equation for this, okay? So remember iron 3 oxide, it doesn't mean that it's iron is Fe, it doesn't mean that it's Fe3O, that's incorrect, okay? It means iron 3, that Roman numerals 3, it means iron has a oxidation state or a valency of 3. Oxygen, iron oxide, is 2 minus. So when I write the formula for iron oxide or iron 3 oxide, then the formula is going to be Fe2O3. Fe2O3. That's how you write a chemical formula for an ionic substance, a metal mixed with a non-metal, or metal reacting with a non-metal. You put the 2 on that side and you put the 3 on the other side. That's how you always get the formula. Okay, so let's write a balanced chemical equation. What are we doing? We have our iron ore, which is iron 3 oxide, and it's being reduced by carbon monoxide. So fancy words, all it means is Fe2O3 is being reduced. So it means it's a redox reaction, but you don't really have to know anything about redox reactions. It's being reduced by carbon monoxide. So that means it's just CO, not CO2. And what are we getting? It says that we are getting iron and carbon dioxide. So iron is Fe and carbon dioxide is CO2. So often they'll give you the equation in words. So they give you the products. You won't be expected to know that iron oxide plus carbon monoxide is iron and carbon dioxide. You don't have to learn that off by heart, okay? They will give you the reactants and the products. So on the left-hand side is the reactants, and on the right-hand side, that is the products. Okay, so now we're going to just check if it's a balanced chemical equation, okay, because it might not be. So look on the left, we've got 2 Fe because it's Fe2. So on the right, we've only got 1 Fe. So that means we've got to put a 2 in front of that Fe. Okay, that's how you balance equations. You put a number in front. You can't ever put a number over there. That would be incorrect when you're balancing equations. When you're writing formulas, that's where your numbers go, but not when you're balancing equations. Okay, so now our ions are balanced. Our Fe is balanced. What about our carbons? You can see on the left-hand side, there's just C, and then on the right-hand side, there's just C. So there's 1 carbon and 1 carbon. Okay, so our carbons are balanced. Right, what about our oxygens? They don't look balanced to me. We've got 3 oxygens over here and 1 oxygen over here. That makes 4. But on the right-hand side, we've only got 2 oxygens. So how do we make 2 oxygens become 4? We've got to put a 2 in front. Okay. So now we've got 4 oxygens, but now we've got 2 carbons. So we got to put a 3. So now we've got to put a 2 in front of here. Oh, I shouldn't have given you such a complicated one. And then, so now we've got 2 carbons on the left and 2 carbons on the right, but now we've got 4 oxygens on the right, but now we've got 3, 4, 5 oxygens on the left. Okay, so goodness me, what are we going to do? We might need to put a 2 in front of our Fe. Sometimes this is a bit of trial. So there we've got 4 Fe's and we've got 6 oxygens plus another 2, which is 8 oxygens. Okay. 6, 7, 8. And then on the right, we've got 4. So that's not balanced yet. What do we need to do? Did I read the question correctly? Fe2, yes, oxide, carbon monoxide. In the blast, we've got iron and carbon dioxide. Yeah, we've got that right. Okay, so we need to put the 2 there, then we need to put a 4 there. Okay, so then we need to put a 4 there. We need to put a 4 there. 6, 7, 8. And then we've got 8. Okay. So hopefully that will do it. Right. Calculate the mass of iron produced from 1 kg of iron 3 oxide. Okay. So what's very important, no, these are not, this is not balanced yet. What do we, maybe we need to put a 3 here. So we've got 9 oxygens, 9 plus 1 is 10. And then we need to put 5. Goodness me. Okay, I'll have to come back to this one. I've got another mass one, don't worry. Another one with mass. That was, there we go. Right. What mass of iron 2 sulfide is formed? I'll come back to that one, sorry, I need to think about it. Normally I have my notes with me. What is the mass of iron 2 sulfide? What mass of iron 2 sulfide is formed when 5,6 grams of iron is completely reacted with sulfur? So we need to have a chemical equation. So iron, oopsie, moved on to the next page. We've got iron that's reacting with sulfur. And what do we get? It says, what is the mass of iron 2 sulfide? Okay, so that means it's Fe2 plus. Okay, that's what iron 2 sulfide means. And then what is sulfide? What group is sulfur in? Because sulfide is sulfur. And we'll go back to the periodic table to remind ourselves what group sulfur is in. It's in group 6. So that means it has an oxidation state of 2 minus, same as oxygen. Back to the volume 1 now. Okay, 2 minus. So Fe, so if I write that, the simplest formula, for every 2 ions, I need 2 sulfur. So for every 1 ion, I need 1 sulfur. So the formula for iron sulfide is just FeS. And you can see that's a balanced chemical equation because I've got 1 ion on the left and 1 ion on the right, and 1 sulfur on the left and 1 sulfur on the right. Okay. So it's asking us, what is the mass of iron 2 sulfide formed when, so they want to know how much of this are we going to get? And this is what stoichiometry is all about. How much of that are we going to get in grams, in mass, when I have 5,6 grams of iron? Okay, so I've got 5,6 grams of iron. Now, how much iron sulfide am I going to get? Okay, so note how I wrote the mass of what we were given under the element concerned. So we were given iron, we were given 5,6 grams of iron. So in order to do these calculations, you always need to use the number of moles as your to work from. So our first step, now that we've deciphered what the question has asked us and we've written a balanced chemical equation, we now need to work out the number of moles. So the number of moles of iron is going to be our mass. Remember, so I'm not going to write the formula all the time, but remember, number of moles is mass divided by molar mass. Okay. So the mass of iron the guy gave us is 5,6. The molar mass of iron, got to go back to the periodic table and check, because we're not expected to know that off by heart. We've got to go look for iron in the periodic table. Fe, it's 56. Okay, 56. So we're going to divide there by 56. Okay, so that should be an easy sum. 5,6 divided by 56 is 0,1. 0,1 moles. Okay, now moles is not M, moles is MOL. Okay. Now, once I have the number of moles of iron, this is what we were given. Now we can work out the number of moles of iron sulfate. So pay real close attention now. How do I do this? Okay, I look at what's called the mole ratio. Okay, so this is a balanced chemical equation. So in front of this iron is a 1, an invisible 1. And in front of this iron sulfide is an invisible 1. That means, what is my ratio from going from iron to iron sulfide? My ratio is 1:1. Okay, that means if I have 0,1 moles of iron, then it means that I'm also going to get 0,1 moles of iron sulfide. So I have to use the mole ratio to work that out. Okay, that's why I've got it in a different color now. I had to work out how many moles of iron sulfide I'm going to get. Okay, so the first step is to work out the number of moles of what you have, which was our iron. Then we've got to look at our mole ratio. What is the ratio between iron and iron sulfide? Okay, so for every 1 iron we use, one mole of iron we use, we're always going to get 1 mole of iron sulfide. And for every 1 mole of sulfur we use, we're always going to get 1 mole of iron sulfide. Okay, so if I've got 0.1 moles of iron, then I'm going to get 0.1 moles of iron sulfide, because that is the 1:1 ratio. So now if I know the number of moles, I can then work out the mass, because that's what the question asked. They asked for what mass of iron 2 sulfide would I get? Okay, so I now know that the number of moles is 0,1 mole. Therefore, I can work out the mass. Okay, now I'm changing this formula around, and the mass would be equal to the number of moles times by the molar mass, because what do I have to do to get m, small m by itself? I have to times by capital M. Or you can use your nice easy triangle. And our easy triangle was that the number of moles, sorry, I'm running out of space there. I think I've got an extra page, yeah, may as well use it. Using this triangle. The number of moles is equal to the mass divided by the molar mass. So if I want the mass, then it means that mass, that's how you read the triangle, is now N times M, capital M. So that stands for molar mass. Oops, let's go back. So now I can work out the mass. Let me go back to my green color. It's 0.1 moles times the molar mass. Now remember, it's the molar mass of iron sulfide that I'm trying to work out. And iron sulfide, what did we say that iron was? It was 56. And what did we say that sulfur was? I think it was 23, but I can't remember. Let's go back to our periodic table. I mean, we should, when we're doing an exam, we should always double check and not rely on our memories. Oh, so it's 32, not 23. Luckily, we didn't rely and iron was 56 and 32, 56 and 32. So that means the molar mass of iron sulfide, we have to go and add that. It's 56 plus 32, which is 88. So I'm going to put 88 there into my formula. 0.1 times 88 is going to give us 8.8. And remember, we're working out the mass, so it's going to be measured in grams. So we're going to get 88 grams of iron sulfide. 88 grams of iron sulfide. So you can see there's a lot going on. This is worth a lot of marks because you've got to calculate. Let me see how many marks it's probably worth. You've got to calculate the number of moles. So you've got to do this, which is worth 1 or 2 marks. Oh, you've got to, first of all, write down a balanced chemical equation, which will be 1 or 2 marks. Then you're going to work out the number of moles of what you were given, which is iron, which is 1, 2 marks. Then you've got to work out the number of moles of your iron sulfide, which is another, that will only be about 1 mark. Then you're going to work out the mass. Okay, so that would probably be 2 marks because you've got to work out the molar mass as well. So 1, 2, 3, 4, 5, 6, at least 6 marks. It could even be more, depending on where they allocate the marks for your calculations, but at least 6 marks. Okay, so let's try practice that a little bit. Okay, that's theoretical yield. Go to that. Let me give another example. Let's make an example. If I have some sodium and I react it with water, I'm going to get hydrogen gas and sodium hydroxide. Okay, so I'm giving that to you. You won't need to do it. Let's check if it's balanced. We've got 1 sodium on the left, 1 sodium on the right. We've got 1 oxygen on the left, 1 oxygen on the right. We've got 2 hydrogens on the left. We've got 2 here plus 1 there. So it's 3. So we need to balance our hydrogens are not balanced. Okay. So if we put a 2 in front of the water, on my highlighter, I want my pen. If we put a 2 over there, we're going to have 4 hydrogens on the left-hand side. And then on the right-hand side, I've got 3. So I'm going to have to make it 4. So I'm going to put a 2 over there. Okay. So now I've got 2 sodiums on the right, 2 oxygens on the right, and then 2 hydrogens plus these 2 hydrogens, which makes 4 hydrogens on the right. Okay, so let's check the left. I've got now 4 hydrogens, which is balanced. I've also got 2 oxygens now, because remember this 2 is for the H2 and it's for the O. So it means that there's 4 hydrogens, and that means that there's 2 oxygens. That's how it works. Now my sodiums aren't balanced, but all I have to do to balance my sodiums is to put a 2 in front of that. Now, if you check it, it's going to be balanced. Right. So let's say I use 20 grams of sodium. I cut a piece of, I always do this experiment in my classroom. If I cut a piece of 20 grams of sodium, and how much hydrogen gas am I going to get? Okay, how much hydrogen gas am I going to get? So what is the mass of the hydrogen gas? gas we could measure in volume, maybe it's a little bit better, but let's work for mass for now, just so that you can get used to all of this. So this is what I'm given. I'm given my equation, then I make sure it's balanced, and then I'm given the mass of sodium. So look how I do it. I always work underneath the elements or the compounds involved in the chemical equation. So now I have to work out the number of moles of sodium. Okay, so remember the number of moles is the mass divided by the molar mass. So it's the mass of sodium, which is 20, they gave it to me, divided by the molar mass of sodium, which is, I think that was what 23 was. I don't know why I've got 23 in my mind today. Yes, sodium, 23. Remember, you get that from the periodic table. Okay, so we're going to say divided by 23. I wonder if there wasn't a typo in another question. So I can't balance it. 0.87. 0.87 if I round off to 2 decimal places. Now this is moles. Okay. So now they gave me the mass of sodium. Then I had to work out the number of moles of sodium. Now once I have the number of moles, now I can work out whatever else I need using a mole ratio. So what did they want? They wanted the amount of hydrogen that I'm going to get. Okay, and I said we're going to keep it to mass for now. So now I have to use the idea of the mole ratio. So the ratio of sodium to hydrogen, according to my chemical equation, is 2 to 1. Where am I getting that from? Okay, the fact that I know from my balanced chemical equation, where's my highlighter? And I've got 2 sodiums and I've got 1 hydrogen. Remember, you're looking at the coefficients. Okay, hydrogen is always H2. So it's not 2 to 2, it's 2 to 1, because I've only got, for every 1 sodium atom, I have 1 hydrogen molecule. Okay, or for every 1 sodium molecule, I've got 1 hydrogen molecule, if you want to think about it like that. So that's why the ratio is 2 to 1. It's not 2 to 2, and students often get confused. They see this 2, and then they think the ratio must also be 2 to 2, but it's not. Okay, you only look at the coefficients in your balanced chemical equation. So there is an invisible 1 there, because if I just have H2, it means that I only have 1 H2. Okay, so the ratio is 2 to 1. That means if I've got, now I worked this out, 0.87, if I've got 0.87 moles of sodium, then how many moles of hydrogen am I going to have? What do I have to do? I have to say 0.87, and I have to divide that by 2, because the ratio is 2 to 1. Okay, so if I have 2 to 1, and I've got, if I had 4 here, then it would be 2 there. Okay, just showing you using simple numbers. Sometimes decimals can confuse people. So I'm going to say 0.87 divided by 2, and I'm going to get 0.435. So I had to work out this number of moles. Remember, that's mole, number of moles. I had to work it out, but I can't use this equation because I don't know the mass of hydrogen. That's what I'm trying to work out. Okay, so I can't use the normal equation that we've been using to work out the number of moles. That's why I have to use this mole ratio concept. See, we're nearly out of time, so I'm going to finish this one. That's the mole ratio concept. Now that I know the number of moles, now I can work out the mass of hydrogen. So mass is equal to the number of moles times the molar mass. So how many moles of hydrogen do we have? We worked it out to be 0.435. What's the molar mass of hydrogen? Okay, remember the molar mass of hydrogen in the periodic table is 1. That's just for H, but we've got H2. Okay, so it's going to be times 2, and then we're going to have 0.435 times 2, which is going to give us 0.87 grams. So that's how much hydrogen gas we're going to get. Okay. So guys, that's where I'm going to leave it for today. There's lots more stoichiometric calculations involving volume. As you can see, I've got other examples here involving volume, involving concentration. We will continue. Maybe I should have left that slide up just a little bit longer, so that in case you were copying anything down. Sorry, where was it? Not that one. It was a little bit further up. Okay, just in case you were copying anything down there. We're going to be doing more of these just to practice it, maybe one more lesson of all these different calculations. But you can see it's quite involved, and I'm going to talk you through it step by step. So the moral of the story is you need a balanced chemical equation, you need to work out the number of moles, then you need to use the ratio to work out the number of moles, and then you need to then work out either the mass or the volume or whatever they've asked you to work out. We haven't done any examples on volume yet. We didn't get there. So I hope you found this lesson interesting, and I hope that it's useful to what you're doing in class. This is a big section of term 3 work and a big section in your paper 2 examination, these chemical calculations. So this is the first time that chemistry is really getting hard for you and that you have to do these calculations. And we do a lot more of those in grade 11. They get a little bit more complicated. So the foundation that you are building now in grade 10 is important. So guys, yeah, spend some time maybe going through that. I give you examples from Siavula because the Siavula textbooks are free. You can just download them from the internet if you don't know. So I wanted you to be able to access everything that I give to you, and there are lots more ones to practice in the Siavula textbook. So maybe go and read it and download it so that you can do some practice. But as I say, next week we're going to work on volume and concentration. So I hope you enjoyed the lesson, and I just want to encourage you guys, remember science is meant to be hard. It's meant to be a little bit of a struggle, and it's all about problem solving and developing our problem solving skills. So just keep that in mind so that you don't feel defeated. It's not meant to come easy. It's meant to be a bit of a fight, and then you know you're really learning. So I encourage you to just keep persevering and pushing through that, and not to be demotivated by the fact that you might think it's hard. So I wish you well in the next week, and I'm going to see you again next Saturday. So thank you so much for your time. And if you need anything, please email me. My email address is on the screen.